First, I would like to thank the organizers for invitations. Actually, the O3 sigma model is equivalent to the CP1 model, so the same title, not different. Let me briefly introduce our models. In the theoretical physics, in the classical O3 sigma model is described by three scalar fields satisfying this condition, and this is known to be useful for Heisenberg ferromagnet. For this model, the classical solution is well known in the 1970s, but the solution is scale invariant, which makes the model is unsuitable for particles. So there have been many attempts to break the scale invariance. Among the physicists, the physicists reached the same conclusion: the introduction of gauge fields. So there appears the gauged O3 sigma models. The first well-known model is the Maxwell-gauged O3 sigma model given by Schroer in 1995, and there are several other models which is used the approximate soliton model for the heavy particles, elementary particles. Another one is the Chern-Simons gauged O3 sigma models given by Gauche and other people. These kind of models are useful for the describing particles which have fractional statistics. And after that, Kim and Lee suggested a model which is called the Maxwell-Chern-Simons gauged O3 sigma model. And they insisted that their model unifies the two, this one and this one. So in this paper we are interested in this model. So the self-general equations for Maxwell-Chern-Simons O3 sigma model can be written after some changes of variables. The system in R2. We briefly write MCS and O3. Here omega and n are functions from R defined on the plane with real values, and coefficients A and Q and kappa are positive, and A is bigger than or equal to 1. And this denotes the Dirac measure concentrated at the point Pj. The point Pj are called the vortex points, and the number Nj is integer. So representing the multiplicity of the measure. And we are interested in this model, but we can also consider a simpler model, which is called the abelian Maxwell-Chern-Simons model, initiated by Lee and Min in 1990. And the models can be written in this system. So actually, the Maxwell-Chern-Simons model was initiated by these people to explain the Maxwell, the unification effect of Maxwell model and the Chern-Simons model in the abelian case. So for the O3 model, these people studied the Maxwell-Chern-Simons model following the idea of these people. So we can compare this system with this system in both physics and mathematics. there are usually we can consider three types of problems for this system. One is the topological boundary condition in R2. Here we want this term to be 0. So if this one is 0 at the infinity, then double equal to 1. Is double equal to 0 at the infinity. This is called the topological condition. Another is non-topological condition, which makes that this term is 0. So w goes to minus infinity at the infinity, and n is equal to minus 1. So another one is the periodic conditions on the flat torus. So in this talk, I will talk about the topological boundary condition. Although so we can consider this system as a generalization of this system with more complicated nonlinearity. And although these systems are seem to be different, they share lots of things. In fact, we can find a unified form like this one. In the Maxwell-Chern-Simons O3 model, the function f is given by this function, and in the Maxwell-Chern-Simons model, f is given by this function, linear function. So we can write in the unified form. So in this equation, if we take this limit, kappa tends to be 0, and the function, this is called the neutral scalar function, and is identically 0, then this term vanishes and this term vanishes. So we have this single equation, which is called in the Maxwell-Chern-Simons case the Avalanche model, studied by Jaffe and Tabus in 1980s. And for the Maxwell-Chern-Simons O3 model, this corresponds to the Maxwell-gauged O3 sigma models initiated by physicist Schurers and studied by mathematician Yang. And on the other hand, in this equation, if q goes to infinity, let me consider the case that q tends to be infinity. So the former one is called the Maxwell limit, and in this case it is called the Chern-Simons limit. Then if q goes to infinity, this term must vanish formally. So we have this identity. Moreover, since q goes to infinity, this term also vanishes. So we have q times this term must be this identity, this quantity, and n is equal to this one. So we have formally these identities. So we can finally derive formally the single equation from this one. So we replace this term by this one. So this is, in the Maxwell-Chern-Simons case, this is called the Avalanche-Chern-Simons model, and studied many people. This model was initiated by physicists, two groups of physicists in 1990, and many people, many mathematicians studied this model, including Professor Lim and Che here. And for the Maxwell-Chern-Simons O3 model, this corresponds to the Chern-Simons-gauged O3 sigma model. So initiated by physicists Kim, Lee, and Lee in 1996, Schurers 1996, and studied by these mathematicians. So the Maxwell limit and the Chern-Simons limit is the very formal process. Actually, physicists insisted that by this limit, two limits, the Maxwell-Chern-Simons limit unifies the Maxwell model and the Chern-Simons model, but the argument is very formal. So my interest is on the rigorous proof for this kind of limit. So the problem is we have three problems. The first one is existence, and the second one is the proof Maxwell limit, and finally the proof of the Chern-Simons limit. So since we can consider this system as a generalization of this system, let me first investigate this system first. For the Maxwell-Chern-Simons models, in the topological boundary condition, we have a result given by Chen and Kim in 1997. First, they show the existence of variational solutions, and also they show the existence of maximal solutions given by some using the super and sub-solution method. In fact, we can easily find the super solution, but it is difficult to find a sub-solution. So they use the monotonicity of a function. In fact, if you find if G is a function associated with the equations, then if the iterative sequence has pointwise estimate like this one is bigger than this one, and this one is bigger than this one, then we can obtain the monotonicity of the functionals. From this one, we can obtain boundedness of H1 boundedness of the iterative sequence. So, these two ones are concerning the existence of solutions. For the Maxwell limit, they show that for the arbitrary sequence, prove the Maxwell limit for the arbitrary sequence. That means that if W kappa and kappa is a solution of the Maxwell-Chern-Simons model for corresponding to kappa, they converge it to the solution of Maxwell-gauged model, and n goes to 0. But their method heavily depends on the iterative scheme. That means that first, it is easy to show that every solution is less than or equal to the Maxwell-gauged solution. Then, using the monotonicity of a functional, they can find the boundedness of the H1 norm of solutions. So their proof requires an iteration scheme. For the Chern-Simons limit, they prove the.
So this omega k and omega kappa and kappa is the maximum solution.
No, arbitrary solutions.
But that's why this almost is like you have condition, right? Together with the you have condition.
Yeah.
There, this implied solution is the maximum solution.
No. Actually, this kind of monotonicity holds if the two functions have the pointwise monotonicity condition. So from this one, we can just obtain this inequality. For the Chern-Simons limit, they only prove it for maximal solutions, not arbitrary solutions. Actually, for fixed, if we fix kappa and write WQ and NQ for a given Q, then they converge to these functions. But they use the monotonicity property of the solutions with respect to Q. In fact, if Q prime is bigger than Q, then they satisfy this monotonic condition. So actually they have an upper bound. So we can find the we can conclude the convergence of solutions. But in this case, we have to compare two equations about WQ and WQ prime. So we need also an iteration method. However, for our model, Maxwell-Chern-Simons O3 model, the iteration scheme does not work in general. So the first result was given by myself and Nam in 2005. If there is a constant kappa 0 satisfying that for each kappa between 0 and kappa 0, there is a constant q kappa, such that our equation or limit maximum solution for q bigger than this one. And the function, these quantities, they decay exponentially at the infinity. So they satisfy the topological boundary condition. The constraints for kappa and q come from the iteration scheme and finding a sub-solution. So in general, we cannot apply the method given by Chen, not Kim, to the Maxwell-Chern-Simons sigma model. So we need a different argument. So our purpose is to show the existence of topological solutions for arbitrary kappa and q, and prove the Maxwell limit and Chern-Simons limit. In fact, for Maxwell limit, we need to kappa goes to 0. But in the case, if kappa goes to 0, then q goes to infinity, not fixed. So we cannot consider the Maxwell limit for this situation. So we need the existence of solutions for arbitrary kappa and q. There are other results for Maxwell limit and Chern-Simons for Maxwell-Chern-Simons model. For example, the topological solutions, and for the period case, and also period case by Richard and Professor Chang and myself for non-topological solutions. So we have three solutions, three theorems. The first one is the existence of solutions for arbitrary kappa and q. And theorem 2 says that verifies the Maxwell limit for fixed q, and we can, if we write u kappa and, this is w kappa and kappa be any solution pair for the Maxwell-Chern-Simons O3 model, then we can find the function u star, which is the unique solution of Maxwell gauged O3 sigma model, such that u kappa tends to u upper star, and kappa goes to 0 in any Sobolev node. So we proved that the Maxwell limit for arbitrary solutions. But for the Chern-Simons limit, we did not succeed in proving that the limit for any solutions, but the solutions obtained by theorem 1. So for fixed kappa, if we write the, this is also WQ and NQ, a solution pair corresponding to Q, then as Q goes to infinity, we can find the subsequence converging to U star and N star. And U star is the solution of the Maxwell-Chern-Simons O3 sigma model, and N star satisfies this condition. So let me briefly introduce the ideal proofs. So for this, we need some regularization, so to remove the singular terms on the right-hand side of equation. So if we introduce a function v0 mu, then it satisfies these equations. So if we change variables like this, then we have a regularized version of our equations with these boundary conditions. So an interesting one is that we can express n from this equation as a function of v, like this one. So we can obtain the fourth order equation about v, which is Euler-Lagrange equation of this functional. So we want to find the global minimizer of this functional. Actually, this method was used for the Maxwell-Chern-Simons model, but the proof of coercivity of functional is very subtle compared to the Maxwell-Chern-Simons model. So the Ebc theorem is as follows. There is a constant mu0 such that the functional has a minimizer in H2 for a large mu, and mu0 is independent of kappa and q. So it is easy to see that the f is weakly lower semi-continuous. So we have to prove that f is coercive. So we have L2 norm of Laplacian v and gradient of v. So we need a bounds for the L2 norm of v, which comes from this term. But e to the v0 implies that this function. So at the vortex points p0, the e to the v0 vanishes. So this term, we cannot extract the L2 norm of v directly from this term. So we need some manipulation. So this term is written explicitly like this one, and we can divide it in two terms. So this term is has a low bound by this term, and this is the norm function with the L2 norm belonging to L2 space. So we have this one, and if capital T satisfies this number, satisfying this inequality, then we can have a low bound of this integral like this one. And actually this one is also comes from the inequality of this type. This which is very useful in gauge theories. So we need to extract the L2 norm of v from this integral. To do this, we will use this inequality. Actually, we can find this inequality from the well-known inequalities. V integral of v square is decomposed in v times v divided by this quantity and v times this quantity. So we have some L2 norm. When we use L inequality, then we have this L2 this integral multiplied by v square and v fourth. So the first term is can be expressed by the L2 norm of v and gradient of L2 norm. So we have after Young's inequality, using Young's inequality, we have obtained this inequality. So we to have a bound of L2 norm of V, this term appears in the functional. So we need to control this term. Unfortunately, this term appears here. So after some calculation, let me skip this one. Then we can finally obtain this inequality. So this inequality, this integral has a low bound for this term, from which we obtain this inequality. And finally, the last term in the functional can be estimated by this. So we obtain this one. From this, f is to be shown. It is shown to be coercive. The second topic is the Maxwell limit. So for fixed Q, we take a large mu and fix it, and write V0 mu and G mu, and let the V kappa and kappa be a solution pair corresponding to kappa of the regularized equation. Then, as kappa tends to be 0, we have this convergence. Here, alpha is a number between 0 and this number. And the V0 is V star is the unique solution of the regularized Maxwell-Gate O3 model. So the main strategy is the use of maximum principle. Although our model is a system of equations, they allow various kind of maximum principle structures. So we don't rely on the iterative scale, as in the Professor Che and Kim's result. So first, we can show that by maximum principle that this quantity is less than or equal to 1, and n is negative, this term negative. So from this one, and we obtain the low bound of n. So n is uniformly bounded function. Moreover, n tends to be 0 uniformly, and the ad infinity norm of V kappa is bounded. Actually, this one is to be shown, and moreover, we can apply the maximum principle to have this one. So to see this, it suffices to have a low bound for this uniform low bound for V kappa. So if Y kappa is a minimum point of V kappa, going to minus infinity, then by the maximum principle we obtain this inequality. And if kappa goes to 0, then from this one, this goes to 0. We have, and this have 0. But by this, this is equal to 0 by this assumption, and this is less than this one. So if mu is large enough, then this quantity is negative. So we have a contradiction. So V kappa must be bounded uniformly. Then with these informations, we can show that the H2 norm of n kappa tends to be 0 as with the convergence speed kappa square. So integrating our equation, we can obtain this integral identity. So this integral vanishes as kappa goes to 0. So we can expect that the L1 norm of n kappa goes to 0 with the speed of kappa square, but this term vanishes at the voltage points. So we need some, we split this integral near the two pieces, or integral near the voltage points and the integral outside voltage points. In the outside of voltage points, this quantity has a low bound, so we see that in that area the L1 norm of this function tends to be 0 with the speed of kappa square, and for the integral near the voltage points, we use this quantity. So we finally obtain the L1 norm. We obtain an estimate about L1 norm like this one. And using this one, we can show that the L2 norm of n kappa and the L2 norm of Laplacian of L n kappa is uniformly bounded by kappa square with times constant. So by the Calderon's inequality, we obtain this estimate. Then in the third step, we show this estimate. We can obtain this equation from the Maxwell-Chern-Simons O3 model and the Maxwell O3 model, and multiplying this equation by this quantity, we obtain this inequality. So as in the former case, this term vanishes at the voltage point. So as in the existing part, we divide this integral in two pieces and made some calculations, and finally we obtain this inequality. From this one, we obtain this estimate, and this estimate implies this one from the equation. So we obtain this estimate. So for the higher norms, we can use induction. Then the proof is complete. Finally, we consider the Chern-Simons limit. In this case, kappa and mu is fixed, and given kappa, we write v kappa and vq, and given q, vq and nq is the solution pair of Maxwell-Chern-Simons O3 model given by the theorem 1, not arbitrary solutions. Then we can extract the subsequence converging to V star and N star. And here V star is a solution of the regularized Chern-Simons model, solution of the regularized Chern-Simons equation, and N star satisfies this one. So in the first step, we show that this estimate. For any given test function, we have this inequality because VQ is a minimizer. So in the case, the function f has a constant q square. So we can eliminate q square in both sides and find this estimate. Then as in the existing part, from this integral, we can obtain the boundedness of L2 norm. And so this one is proved. Moreover, if we add the first equation and second equation, then we can obtain this single equation. Here, n is uniformly bounded, and this is the bounded, and G is uniformly bounded. So we can use the elementary elliptic estimates to have this inequality, this estimate. In the second step, we define two functions, VQ and psi Q. Then the first equation corresponds to this one, and the second equation corresponds to this one. Moreover, we can calculate the Laplacian of VQ to obtain this a little more complicated system. And moreover, we can more complicated identity. So here, all the terms are good. That means that all the functions are bounded, uniformly bounded, except the gradient term of V. And for the second equations, all terms are bounded uniformly, except the gradient of V and gradient of N. So at this point, we need on interior gradient estimated like this one. So the if we have this equation in Rn, then we can have a pointwise estimate of gradient U bounded by this quantity. So in the third step, we prove this estimate. Actually, we apply this lemma to this equation. Actually, this one and this one is uniformly bounded. So phi is less than or equal to q. So the Laplacian of the ad infinity norm of this term is bounded by a constant q. So this term is bounded by q, and this one are uniformly bounded for every ball. So by this lemma we obtain this one. Then you can apply the maximum principle to our equation about VQ to obtain this inequality. We have a constant Q here, and also by this inequality we have a Q. This term here, sigma Q is bounded by Q. So we obtain we see that this term is uniformly bounded. Then we go back to our equation again here. Since this is uniformly bounded, the Laplacian is uniformly bounded. So going back to this lemma, this term is uniformly bounded. So we see that the VQ Laplacian of the gradient of VQ is uniformly bounded. We can apply the similar argument to the equation of psi q to obtain the desired estimate. Let me skip it. So by step 3, we can extract a convergence subsequence in C1 log of R2, and the limit function satisfies the Chern-Simons equations, and the convergence of higher norms follows from the induction. So let me stop here.
Question?